Hi, welcome to video notes 9.2. Let's talk about equilibrium, calculate concentrations, calculate Q. So read section 17.1 through 17.6 and do self-check exercise. So far we know how fast a reaction can go because it's based on collisions. We know what makes a reaction go because we know the driving forces. So if there's a delta G going on, reactants can turn into products, products can turn into reactants, or both reactants and products can turn into each other. Why does that happen? Well, if you have a negative delta G, you're going to get reactants turning to products spontaneously. If you get positive delta G, you'll get no forward reaction, but only the reverse. But what if delta G is 0? That's when the reverse reaction and the forward reaction can happen, and we can get equilibrium. So what is equilibrium? Equilibrium is when the rate of the forward reaction and the rate of the reverse reaction equal each other. And at equilibrium, you have some of everything, some of each reactant and some of each product. Because reactants are turning into products at the same rate products are turning into reactants. So if you have people live in here and people live in here, and the same number of cars go across that way as that way, then the number of cars over here doesn't change, and the number of cars over there doesn't change, but the cars are different each time because they're going back and forth at the same rate. Okay, kind of like sugar in iced tea. If you put too much sugar in your iced tea, you're going to get sugar on the bottom. But all of these sugar molecules are not the same ones each time because the sugar will dissolve at the same rate that the dissolved sugar will precipitate out, and so you get an equilibrium of deposition and solid forming and solid dissolving at the same rate. So it looks like the solid's not changing, and it tastes like the dissolved sugar's not changing, but it is changing at the same rate. So we call equilibrium dynamic equilibrium because dynamic is always changing and never stops. So when you first start a reaction, the rate of the forward reaction is pretty quick, but then it starts to slow down. The rate of the reverse reaction is pretty slow when it starts because there's no reactants, but then it starts to speed up once products start to form. Okay, and then when the rate of the forward and the rate of the reverse are equal, you have equilibrium. So what might that look like in terms of amounts? So reactants turn into products, so their concentration goes down. Products turn back into reactants, but at first there are none, so their concentration goes up. But once the amounts are not changing anymore, then you have equilibrium. Okay, how does this represent that? Well, the rate of incoming water equals the rate of outgoing water. But guess what? None of these water molecules are ever the same because these new ones are replacing those old ones, but it looks like the amount's not changing. Same with this, equilibrium. You got incoming, you got outgoing. And so these water molecules are new, the old ones leave, but the amount of water molecules doesn't change even though the actual water molecules themselves are different. Okay? So we can quantify this by doing what's called an equilibrium constant expression. Equilibrium expressions, I'm going to write the word constant in here, okay? Because when I say it, write an equilibrium constant expression means write a K. So how do you do that? Well, since the amounts in the container don't look like they're changing, you can take a ratio of the amounts of products to the amounts of reactants. How do you do that? Well, you do the concentration of products raised to their coefficient power divided by the concentrations of reactants raised to their coefficient power. So what is K? K is the equilibrium constant. R are reactants, P is product, and the brackets mean molarity or concentration. This means coefficients. Coefficients. All right. So another way to say that is just check out your balanced equation. If you want to write an equilibrium constant expression, you put the products on top over reactants, and look, it's multiplied. These are multiplied. There are no addition signs here. The brackets times the brackets. And then these are the coefficients, right? Coefficient, concentration, right? Coefficient, concentration. All right, now, when you're writing a equilibrium constant expression, pure solids and pure liquids aren't part of the concentration. Because if you have a pure solid or pure liquid and you want to know how many moles, the volume doesn't really change, right? So we have a certain number of moles in a certain volume. No matter if we cut that in half, we have a certain number of moles in a certain volume. So the concentration is 100% concentrated. Then with liquids, 100% concentrated. So they're not part of the equilibrium constant expression because they're not changing their concentrations. They're packed together. Density doesn't change. Okay, so we have to be able to write these. So I'm going to have you do this one, and I'm going to do this one here. Okay, and you're going to do number 2. So the equilibrium constant expressions take the products. We have ions, Fe plus 2, right? And the coefficient is 2, so we got to raise it to the power 2. Times I2. But notice I2 is solid, so I don't have to put it in my equilibrium constant expression. Okay, on this side I have aqueous iodide ion, so I minus for the species, and then to the second power, because the coefficient is 2, times, I know that's a plus sign, but in the equilibrium constant expression we have to multiply, iron plus 3 ions to the second power. Okay, you do these two, and we'll check them in class. Alright, now, the truth is not all reactions are at equilibrium automatically, but if it can go to equilibrium, it's on its way. So sometimes we take a ratio of products to reactants at any time, and we call it Q because we don't know if it's at equilibrium. Formulas for Q is the same as K, but we aren't sure if it's at equilibrium, so we call it Q. So if we look back here, oh, it's a K because we know equilibrium. Look over here, it's called a Q because we don't know if it's at equilibrium or not. So once you check the Q, you know it's at equilibrium if it equals the K. If the Q is bigger than the K, then we're taking this ratio of products over reactants. If the Q is bigger than the K, then there's too much of this. All right? And so in order to get to K, it has to go down. So then it has to shift towards reactants. Because remember, in reactant products over reactants, if we want this to get bigger, we have to shift that way. Okay. Now if Q is less than K, the product over reactants again. So if this number is too small, this number has to get bigger. So it has to get more of the top number, and so it has to shift towards products. Right? So Q can tell us information about how close to equilibrium we are, or which way we have to go. Okay. But look, it's a problem to work on. The equilibrium constant for the reaction is 7.1 times 10 to the second. That is our K. Right? But our equilibrium constant expression is products over reactants. So we have HI to the second power divided by I2 divided by H2. Right? So it's got to be products over reactants. So we know that this is K, but we don't know if we're there yet. So we would take our concentrations given and plug them in. So 0.81, we have to square that, divided by 0.44, divided by, oops, I lied, that's not 0.81, that was H2. This is 0.58, okay, divided by 0.41, which is I44, divided by 0.81, which is I2. Oh my goodness, that was H2. Come on, Harbin, get it together. Alright, so we plug those values in, and we find out the answer to that is, I did this already, is 0.94. 0.94. What does that mean? So 0.94 is our Q, and it is smaller than 710, which is 7.1 times 10 to the second. That's our K. So what does that mean? It means we're not at equilibrium. Nope, not yet. But it needs to get bigger. So in order for this number to get bigger, we need more of the stuff on top, and more of the stuff on top is product. So we'll shift toward more products. to get to equilibrium, to get to, all right, look, it's another problem. We have this reaction, and we know it's at equilibrium. Here's some concentrations. What is K? K is the equilibrium constant, all right? So let's write the expression. N2O5, we gotta square that, divided by NO to the fourth power, divided by O2 to the third power. All right, let's put in some numbers. N2O5 is 8 molar. All right, let's split that. Divided by O2, which is 3 to the third power, divided by NO, which is 2 to the fourth power. So we find out that this is 0.148, which is that. Okay. All right, that's K and that's Q. And now we got to get even more detail. Okay, so, oh look, it's a balanced equation. And it's talking about equilibrium. And the question is, what will be the equilibrium concentration? So we want to find out this about everything, because at equilibrium, there's some of everything. Okay. So you should write an equilibrium constant expression. You would put the products, H2 times I2. Look, it's multiplied, divided by HI. They're all gases, so we're all safe. All right. And we know that's going to equal 0.016. So this is called an ICE table. ICE. Right? ICE table stands for initial concentration, the change that's going to happen, and the equilibrium concentration. Okay. So let's ice up HI. So we need to find out what the concentration of HI is to start. Well, it's 0.4 moles in every 5 liters, so it's 0.8 molar. Okay. What's the concentration of hydrogen at the beginning of a reaction to start with initially? None. How about I2? None of it. Okay. Let's see how it's going to change. Well, if there's some of everything at equilibrium, then some of this is going to go away. So the 0.8, so the change is going to be this going away, and it's going to go away at a rate of 2x, right? So what's going to happen to H2? Well, H2, there has to be some, so we're going to call that x. And I2, there has to be some, so we're going to call that x, because you have to get some. And every time you get one of those, you're going to get one of those, because it's the ratio of moles. And that happens every time 2 of those goes away. So if this is x and this is x, that's 2 times x. All right. So at equilibrium, we're going to have to, what we started with minus the change gives us equilibrium. What we started with plus the change. What we started with plus the change. All right, so now we can plug those into our equilibrium constant expression. So I'm going to say x times x over 0.8 minus 2x, and I have to square that because look, it's squared. And this is really x squared. So what's cool about this is it equals 0.016. Right? And since it equals 0.016, and this is a square and that's a square, we can take the square root of both sides. So if I take the square root of 0.016, I get, so I could square this side, square root that side, 8.12649. Yeah, it's going to be equal to x over 0.8 minus 2x. So now I multiply this on this side. I'm trying to solve for x. And so I'm going to get points 1011. Let's see, 92885 minus 2 times that. X. So we get 0.252 982216 x equals x. Alright, so now I gotta get x's on the same side. So I gotta add point blah blah blah. And so I'm gonna get x So equal 0.08076. All right. That's what X equals. But it says what will be the equilibrium concentration. So at equilibrium, we're going to have X of H2. So H2 concentration is going to be equal to 0.076 molar. The I2 concentration is also X. That's going to be 0.08076 molar. And then the HI concentration is, plug in for X, 0.08076. And I find out, so 0.8 times 2 minus that is, let me see if I get it. The hydrogen ion concentration is, hydrogen iodide concentration is 0.8 minus 2 times 0.08076. 0.63848 molar. Okay, so now I know what will be the equilibrium concentration of each species. I just did it. Okay. This one, we're just going to send up the ice chart because we have to be able to figure that out. Okay. So we get 0.6 moles of NO and 0.75 moles of O2, and they're placed in a 2-liter flask. Right. So initially, NO, we have 0.6 moles for 2 liters. So the molarity is, let's see, how am I going to find this one? Is 0.3 molar. Right. So these are concentrations. Initially I have that. Initially I have 0.75 moles for every 2 liters is 0.375 molar. Right. But what about this NO2? Well, there's none to start with. Okay. So that has got to change because equilibrium means there's some of everything at equilibrium. All right, so here's our balanced equation, and I want to write a K for this. So K is going to be the concentration of oxygen times the concentration of nitrogen monoxide squared divided by the concentration of nitrogen dioxide squared. Okay, so that's the K expression. We know that equals 0.5. So I initially had this. That's got to change, people. All right, and so if you look at this, if these are going to react, then we're going to get 2 times the amount of the oxygen. And then we're going for this, we're going to get subtracting 2x of that, because some of that's got to go away. But every time 2 of those goes away, 1 of those goes away. So that's a minus x. All right, so that's going to be the change. So the change has to do with the coefficients because it's a ratio. Right? At equilibrium, we have 2x of that. We're going to have 0.3 molar minus 2x of that. And we're going to have 0.375 molar minus x of it. All right. So that means if we wanted to calculate the concentrations, we would plug this in for O2, 0.375 minus x times NO would be 0.3 minus 2x, and then we have to square it because it's part of the equilibrium constant expression, divided by 2x squared. Now, solving that would be complicated, but we know it's 0.50, so we could solve for x and plug it back in and get equilibrium concentrations. Not going to do it, just wanted to set up the ICE table, initial change equilibrium. Okay, here's one that we can do. All right, so we're looking at this. We want an equilibrium constant. Let's write out the formula for the equilibrium expression. HF squared y, because the coefficient's 2, divided by the concentration of hydrogen times the concentration of fluorine. All right, so we're looking for this. Right? So in order to do that, we need to find out what these numbers are at equilibrium, because this means equilibrium. So we're going to ICE it, and we need our HF, and we need some H2, and we need some F2. We need all of that. At equilibrium, there's some of everything. So initially, we had 10 moles in 1 liter. So we had 10 molar of this and 10 molar of that. How do I know? Well, I read the problem. Okay. Also, we find out that when those are mixed together, we get 4.5 moles of HF gas. Right? So initially I didn't have any, but I changed that. So I added 2 times the amount of X for that, and then I took away some hydrogen, I took away some fluoride. Now you might be wondering why these are X and that's 2X. Well, every time one of these goes away, I'm going to get 2 of those. Every time one of those goes away, I'm going to get 2 of those. So if I call these X, that has to be 2X. At equilibrium, I'm going to have 2X of that. I'm going to have 10 minus X of that. I'm going to have 10 minus X of that. But I have some information in this problem that can help me. I know at equilibrium, there's 4.5 moles in every 1 liter of HF. So I already know 2X equals 4.5 molar. All right, 2X equals 4.5 molar because that's how much it makes. So I can go ahead and solve for X. So if 2X equals 4.5, X equals 4.5 divided by 2, which means X equals 2.25. X equals 2.25. So I could plug it in. 10 minus 2.25 at equilibrium. 10 minus 2.25 at equilibrium. So I can go up here and plug it in. I'm going to have 4.5 at equilibrium. Gotta square that. And down here I'm going to have 7.75 times 7.75. And I find out that my equilibrium constant is 0.337. Woo! I did it. Okay, that was a lot. But I want you to know equilibrium is abbreviation for equilibrium, EQ. EQ is dynamic changing. EQ means equal rates. Because they're equal rates, the amounts are constant. You can only change that with temperature. The constant is products over reactants raised to coefficients. Solids and liquids are not allowed. Q is just like K, but we don't know if it's equilibrium or not. And you need to ice your stuff. Create an ice table. All right, so Moltato can't wait to do 17.2. Just do it here. All right, peace out.